All right, guys, welcome back. So we're going to do the exponential part, because remember we were looking at power functions and or polynomials and exponential derivatives in this section. So if you remember, an exponential function looks like f of x equals b to the x, right? Where b is some number. So for example, we could have stuff like f of x equals 5 to the x, all right? Or f of x, comma, here's another example, equals 1/2 to the x. And then we also have our exponential function, e to the x. So just to do a little exploring, if we wanted to find the derivative, we don't know how to do it, but we could definitely use our limit laws. We can go back to chapter 2, and we'd be looking at, b to the x plus h minus b to the x divided by h, okay? And now look at the x plus h. We know with our exponent rules, if we add up the exponents, that's like multiplying this same base. So I'm going to go backwards with that exponent rule, right? Because b to the x times b to the h is equal to b to the x plus h. So we can go both directions, right? And when I do that, now I can factor out a b to the x. Because it's in common. No, that scared me. Okay, so b to the x times this stuff. Okay, look at this right here. We're taking the limit as h approaches 0. B to the x doesn't have any h's in it. So because that's not part of the limit, it's behaving as a constant as far as h is concerned, right? Because the limit as h approaches 0, it's only going to care about terms with an h in it or factors with an h in it. This whole factor doesn't have an h. So it's like we're multiplying the rest of the expression by a constant. So we can actually take this b to the x and move it to the outside. All right, again, because it doesn't depend on h and because, it's multiplying the rest of the factor like that. So it's behaving like a constant. And we know when we multiply a function by a constant and take the derivative, we can just move the constant to the outside. That was this rule. The limit as h approach, let me write it differently. That was one of our properties we saw up above. The derivative of c times a function. Well, we can move c to the outside and then take the derivative of the rest. That's essentially what we're doing. Okay, so now we have this situation where it's b to the x times this. And I'm going to do a little bit of manipulation. Again, we're deriving something. I would never ask you guys to do this, but we're just trying to convince ourselves of the exponential rule. But this is almost like this part right here. I'm going to play around with some zeros. We know that we can add zeros to a sum and nothing changes, right? And then we know for an exponent, if we have b to the 0, it equals 1. So I made those two switches. And why did I do that? Well, now this, what I just wrote, what I just manipulated, is the derivative of our b to the x function at x equals 0. Okay, and then we have our b to the x that we bring down each time. Okay, so what did we show? All right, so again, we're trying to just justify what the derivative of an exponential function is. This is where we started. We wanted to take the derivative of b to the x. We did some clever manipulation, and we said that this is equal to b to the x times the derivative at 0. Okay, so look, the derivative of b to the x is proportional to b to the x. So that's crazy. We haven't seen that before. So we have to ask ourselves, what value of b would make the derivative at 0 equal to 1? Okay, and the reason why we choose 1, because that would just be the most straightforward way of going about it, is if f prime of 0 is equal to 1. Okay? Well, and we can do that. We can do that by looking at rates of changes and doing a table of values, all that stuff. If you want more details for this step, you can refer to the textbook, because it involves a, table and stuff like that. More details in textbook. But you don't need to look at the details to do like homework or to answer a question on the exam. But if you're curious, go read about it. It's good to be curious. Okay, so f prime of 0 is equal to 1 when the base is between 2 and 3. Okay, and we showed that using a table of values. So f prime of 0 is 1. That's just the f prime of 0 is equal to 1. That's the most straightforward way to approach the problem. It's equal to 1 when the base is between 2 and 3. And this is how we develop e. This is where e comes from. This is how we derive e. So going back, here, I'll go up right here. This expression right here I wrote in pink, right, this one right here, we want that to be equal to 1. And it's equal to 1 when the base is e. So let's go down here, because that's a big conclusion. Where does e come from? It comes from calculus and trying to figure out how to take the derivative of exponents. So let's change that base to e. And this is equal to 1. So e is the number that makes that derivative 1. Okay. So that also means, so this is our first conclusion. That also means, let's go back and substitute our base now. We can now substitute e, for that base. And we have our second conclusion. The derivative, of e to the x is equal to e to the x. So if that explanation was a little wacky, and it is, right? It's kind of like magic at this point because we don't have enough theory to really like prove it thoroughly. These are the outcomes that you guys would want. Okay, so from that wacky explanation, kind of get an idea of where it's coming from, but these are the results that we're concerned about. Okay, so there you go. All right. So let's fool around with that. Let's repeat. We know what the derivative of a constant is. We know the derivative of x is, and we know what the derivative of x to the n is. And now we know what the derivative of e to the x is. So let's try this final problem in this section. And we're going to find the first derivative. We're going to find the second derivative. We're going to find the third derivative. For the function is equal to e to the x plus x squared. Okay, so it's a sum of functions, so we can just take the derivative of each term. So the first derivative, what's the derivative of e to the x? E to the x. What's the derivative of x squared? Bring down the exponent, subtract 1. So there you go. Okay, let's talk about the double derivative. What's the derivative of e to the x? What's the derivative of 2x? Whew, let's think. So if we take the derivative, so we can take the derivative of x. What's the derivative of x? We can still use the power rule. We also know the derivative of x is 1. But we can use the power rule, bring down the exponent, and then what's x to the 0? X to the 0 is still 1. So it's going to be 2 times 1 times 1. So the derivative of 2x is just the constant 2. All right, and then we also could have done the fact that we know one of our rules was the derivative of x is equal to 1. So we could have done it like that too. But it's nice to know that we can also prove it with our power rule. Third derivative, e to the x, that derivative is e to the x. What's the derivative of a constant? It's 0. And we can actually, at this point, what if I did this? Crazy nonsense. What if we wanted to find the 10,000th and 32nd derivative? What's it going to be? Well, what's the derivative of e to the x? It's e to the x. So we're just going in circles at that point. So that's kind of fun too. All right, so those are our initial derivative laws. And now in section 3.2, our next section, we're going to be talking about the product and the quotient derivatives, because we don't have those yet. We have constants, sums, and differences. And so we're about to learn what the products and quotients are.